2.
Hello, I'm Brent Donaldson with Additive Manufacturing Media, and welcome to AM In Depth. So AM In Depth is a special series running this week and next week on the IMTS Spark platform. And our goal for this series is to really take a deep dive into issues surrounding 3D printing for production. And sometimes, like today, the best way to do that is to launch you straight into a low Earth orbit. So today we're going to be talking about how a recent collaboration unlocked new ways of thinking about satellite propulsion design, featuring fine, complex 3D geometries that cannot be produced any other way. So joining me now to talk about all of this is a formidable crew indeed. It's my pleasure to introduce, if you're ready, Paul Amon, Senior Staff Engineer at HC Starck, Charlie Burkett, Head of Materials and Applications at HiETA Technologies, Federico Romay, Research Fellow at the University of Southampton, and John Loretto, AMG America's Operations and Application Manager at Renishaw, which is a sponsor of this series. So welcome, everyone. All right, so that was a mouthful. Can somebody tell me if I got all of that right?
Yes, Brent, absolutely right. So this is Federico from the University of Southampton. So yeah, you told us that additive manufacturing enabled a new kind of propulsion technology. So this is true for 3 reasons. The first one is that we have been able to design a single component, but with very complex geometries that you cannot print, you cannot manufacture with other techniques. Secondly, the Resistojet is very small, so there are very tiny features, sometimes on the order of 100 microns. And thirdly, we have produced these with the highest melting point materials on Earth, which is refractory metals. So you see that it's very difficult to find another kind of technology or way to do this.
So, John, Renishaw has had a growing presence in the industrial additive manufacturing space for several years. When did you first learn about this collaborative project, and why is it important for advancing additive's role in the aerospace sector?
Sure, Brent. Yeah, so we were initially, introduced to the project with our friends at HC Starck. It's always great to be a part of a collaborative exercise here where, some of those easy slam dunks for additive are realized, so things like shorter development life cycles for product development and moreover material development on the platform as well. Then obviously, as we're aware, generally speaking, the cost of the complexity of an additively manufactured part doesn't necessarily scale uniformly like it would in traditional manufacturing. So it's great to see that, those 2 big things be very, very simple to obtain with additive. So, but also, moreover, it's great to be on the ground floor of a conversation like this because, we need to, help support the adoption of additive manufacturing in the aerospace sector. So, one of the main limiting things associated with that is understanding the necessities of that industry and any qualification exercises that might be required to get that part into full-scale production, actually get these things into orbit, right? So it's great to be a part of the, the ground floor of that, and we're very fortunate to be with this team here today.
So Resistojet propulsion is a very specific method of spacecraft propulsion that has kind of a unique backstory that dates back to the 1960s. Resistojets have also have potential applications that have yet to be realized. Can someone talk about Resistojets and tell us briefly what your team's collaboration has achieved?
Yeah, so often Resistojets are told as the simpler electric propulsion for spacecraft, which is kind of true when definitely you have a warm gas system. But with our research, we pushed it to the limit, really. So we tried to build a Resistojet that can withstand the highest temperature possible. And we have been able to do this thanks to this collaboration where we really have the ability of using refractory metals. So this is possible thanks to the capabilities of the consortium. So starting from HC Starck that can produce refractory powders, and HiETA that with Renishaw printers can print these successfully. On a note for like Resistojets, so Resistojets are a very popular propulsion system for satellites. In fact, it's the most popular among all of the electric propulsion systems since today. But historically, it has been used with chemical hazardous propellants, hydrogen, for instance. And what we can do with this new technology is really to have similar performances, but without relying on chemicals. So we can use like a much safer gas, heat that up to very high temperature, and get the performance that we need.
So you guys are going to talk about using additive manufacturing to maximize thruster performance for spacecraft propulsion. How has your team approached new design considerations using additive? Was it more of a wipe the slate clean and start from scratch, or did you try to build upon and improve current design through part consolidation and increased performance?
Okay, so I don't want to monopolize this, but basically this Resistojets work started with my PhD back in 2014. And with my supervisor at the University of Southampton, Dr. Angelo Grubisic, we wanted to find a way to produce high temperature Resistojets because we knew that would enable the replacement of chemical propulsion and would change the future of space propulsion. Yeah, we started from scratch, really. But looking into literature, we found out some very interesting research on high temperature Resistojets made back in 60s, 70s. And we basically tried to replicate that using additive manufacturing and reducing massively the amount of complexity of assembly, especially. So we, from many components, we are now using just one single component. So this has been possible thanks to additive manufacturing, definitely. And thanks to also a number of iterations that we had to do to achieve the final requirements of the system.
Okay, so let's dive into this. To our audience members, please note that you can ask questions at any time using the chat panel that you'll see on the side of your screen, and we'll do our best to get to them at the end. So that said, let's begin the presentation, and when we're finished, we'll meet back here and talk a little bit more. Gentlemen, take it away.
Okay, so still Federico here. I'm going to introduce myself very briefly. So I am a research fellow in astronautics in the University of Southampton. As I said, my PhD thesis was on high temperature Resistojets. In particular, we looked into all-electric spacecraft, which is a kind of satellite platform. The University of Southampton is quite a big university in the top 20 in UK. There are above 6,000 staff. Students are more than 20,000. There are 5 campuses, one in Malaysia and the other in the city of Southampton. The good thing about, well, from my point of view at least, of the University of Southampton is that it is very research intensive. And we have some of the best capabilities and facilities in UK. In particular, we have the largest thermal vacuum chamber in UK, which is the one that you see here on the right in the center. And this really is the kind of space simulator that we use to test and qualify the Resistojets, and not just those ones, but also other electric propulsion systems that we research into our research group. So here, I just want to tell you why electric propulsion, so why Resistojet. Simply, electric propulsion allows you to have a much lighter platform, which means that the launcher has to launch into orbit a much lighter amount of mass, which is cheaper. Okay, so electric propulsion came into play already really at the beginning of space commercialization since 80s with the Resistojets. So here you can see on the left an example from Surrey Satellite Technology, which is also a partner of this project. And they have a very long heritage with Resistojets. So here you go with the constellation from Surrey Satellite. At the center, you see instead another example of electric propulsion, in this case for a much larger platform for geostationary. And this is from Boeing and uses another electric propulsion technology called grid ion thrusters. On the right, you also see another example of implementation of electric propulsion from SpaceX, the Starlink constellation, sorry. And in this case, they use another technology in electric propulsion called the Hall effect thruster. But now we need to focus on resistojets. So why do we want to print refractory, or why do we want to use refractory metals? Because they can achieve very high temperature, and in the resistojet world, high temperature corresponds to high performance. So if you look at the equation here, so this is the equation for specific impulse, which is like the performance, like the speed of the system, the performance parameter. And once you have, like here, there's gravity, here's the specific heat of the propellant, and here the molecular weight. So if you consider just one single propellant, then the only way to increase this performance is to increase the temperature. So really, it is very simple to think that you can increase the performance of resistorjet by just increasing temperature, and in particular, from what SSTL, our partner, has that can achieve 800 Kelvin of temperature, we wanted to achieve much more, like beyond 2000. In this way, we can really reduce the mass of the spacecraft of 70% and have massive cost saving. So now the question is, can we produce such resistojet? So as I said in the introduction, we found a very kind of interesting design in literature from 60s, 70s from a company that was collaborating with NASA on developing very high temperature resistorjet using hydrogen. And yeah, the concept is pretty much what you can see here. But what we have done, what I've done during my PhD, is to simplify the manufacturing process using additive manufacturing. So, this is the heater that you can see here. This is the first prototype in stainless steel. And basically it consists of a number of tubular elements that are concentric, and then these are interconnected with some features in inside, and this forms an electrical resistance. But at the same time, you have that the propellant, and you can see that here from this radiograph, the propellant flows from the outer part of the resistojet and then recirculates inside thanks to these tubular concentric elements. And then it's heated by the resistive heating, and at the inlet of this trumpet nozzle, then you have expansion of the gas, and then this produces thrust. So we have been able to make a prototype in stainless steel to demonstrate it, but then the next step was, can we use refractory? So can we really achieve the goal of above 2000 K temperature? So to do this, then we achieved and built this consortium. So Angelo basically made this possible with a project of 2 years funded by QA Space Agency called Super High Temperature Resistor for All Telecommunication Satellites. And the goal is to design and test an engineering model of the resistojet, but not moving from like prototype materials like stainless steel to refractory metals. So the consortium is formed by HC Starck, that provides the refractory powders, then HiETA, that has Renishaw technology to print these refractory metals. We provide the designs, and effectively we also do qualification and testing of the resistojets. And also we have in the consortium Surrey satellite technology that provides us with real mission requirements for the platform. And also we have satellite applications Catapult that provides us with standardizations and secure supply chain strategy. So in order to do this, the first thing that we need is refractory metals. And here I pass it to Paul.
Again, my name is Paul Imone. I'm a senior engineer at HC Starck's Newton facility in the United States. I've been working here for roughly 21 years, so I have a great deal of experience with refractory metals in these types of applications. Traditionally, Starck is a supplier of refractory metals in traditional forms, and we've been working on additive manufacturing components and powders for at least 7 years now. We supply all the refractory metals, tungsten, molybdenum, tantalum, and niobium in powder form. We have global resources to help us with the distribution of the powders, and specifically for this program, to get them over to the to HiETA for the powder building in their systems. And we have extensive support facilities, both in research, R&D, and other traditional processes, for the refractory metals. But now I'm going to kind of move on to the objectives of this program for our company and for the program itself. Overall, as Federico has indicated, improving the performance of the Resistojets, reaching the goals that they have, is going to require refractory metals. So one of the big goals is to develop a new alloy. I'll show you shortly that there's really nothing out there that meets all the goals. But basically develop an alloy to meet the property and performance goals of the Resistojets, and just as important, be able to use additive manufacturing and the laser powder bed fusion process specifically to produce these very complex geometries in refractory metals. At this point, we have supplied pure tantalum and the tantalum 10 tungsten alloy for this work, and we'll be moving on to the alloy development very shortly. So as far as the actual design goals for the materials and the Resistojets, those are shown here. I'm not going to read through them, but you can see they are very aggressive. The goals here, for example, resistivity, you want that very high so that you get efficient heating and limit the amount of electricity you're using for the amount of thrust you're generating. Another important factor is the final two, tensile strength and melt point. Again, as Federico said, one of the only ways really to increase the performance if you have a set propellant is to increase the operating temperature. So we need an alloy that operates at very high temperature, but is still very strong, because there are mechanical stresses involved from the firing of the Resistojet, plus also the thermal cycles as it goes from its operating temperature down essentially to zero due to the very cold temperatures in space. Now, we've done some research to look at what materials are available now, and this is it's very difficult to read, but it basically summarizes our results. The properties required are listed across the top, and anything in green would meet the property requirement listed. So what you can see there is that there's really no one alloy that meets every property target. However, there are two, the tungsten 4 RenAM alloy and the T222. The latter is a tantalum tungsten hafnium alloy. Show the most promise as a starting alloy for further development. For those who are familiar with AM or powder bed processing of tungsten, you'll know that's very difficult. There tends to be a lot of cracking. And we'll see shortly that it's much easier to produce solid components in tantalum. So there we have a competing set of requirements that we're hopefully going to work our way through to give a Resistojet in the highest performing refractory metal we can. For the program, again, as I said, we've had We make many alloys and refractory metal alloys for this program. You can see the requirements that we've put together for powder bed laser powders, kind of based on industry requirements. And we really have no trouble producing any of the alloys listed, and would be able to supply any of these and offshoots of these for this for the project itself. These powders are produced internally. We're using 2 systems to produce powders for this program. We have a small R&D system, which can produce small lots and can do specialized powders. A lot of the work has been conducted on that unit at the moment. And then we've brought online a larger production unit to supply, much larger lot sizes when we begin producing Resistojets in larger numbers. So having the powders, we can then use these in the AM environment, and John Loretto is going to talk to you some more about that right now.
Sure. Thanks, Paul. Much appreciated. Yeah, so guys, as Brent had alluded to, I function as the additive manufacturing group, America's Operations and Applications Manager for Renishaw Inc. Okay, so my background is in material science and engineering. Functionally, I've been in metal additive for probably about 6 or so years. Started off on the service bureau side and then migrated over into now the equipment manufacturer side. So pretty well versed in the technology overall from a user and manufacturer's perspective. So Renishaw is quite unique relative to some of the other equipment manufacturers out there, in the sense that if you look at the company's history, we have a core competency in the design and manufacture of precision metrology equipment. So that comes across in other areas of our business outside of additive. So that's things like our CMM, machine tool, equator divisions, things like that, which are typically more leveraged in the subtractive side of the business. But I'll get into the additive stuff and where those two touch up in a little bit. We also have an expertise in our optical-based measurements, so that comes into play with things like our laser interferometers for precision machine control and alignment, that kind of thing. Mostly for subtractive technologies, but it'll come full circle again. So by consequence of those 2 main things I had alluded to prior, we're very vertically integrated in the sense that anything that Renishaw manufactures utilizes the equipment that we design and build ourselves, internally, right? So, and that's not untrue of any of our additive manufacturing technologies either, whether that's the design and build of the functional equipment that someone would be leveraging to develop that technology with, or product or material with, but also in the sense of how, we can analyze and manage any quality restrictions that might be necessary to keep track of inside the melt pool interaction volume or the process itself, relative like gas flow and things like that, right? So interestingly enough, Renishaw initially adopted laser powder bed fusion into its working scope as a user. Over in the UK, they have a medical dental product division. Okay, so functionally at that stage, Renishaw adopted or bought in to additive to make crowns, caps, molds, removable dentures, that kind of thing with additive. And what we had found during that development phase of our life cycle in the product line was we weren't comfortable or happy with the resolution, accuracy, or repeatability of the platforms, let alone the manufacturing build integrity of the platforms. So we kind of took it upon ourselves to really go full scale, dive into this, and start leveraging the products I had alluded to prior to manufacture our own equipment and then start selling them off into the market scope, right? So from that juncture, been able to throw, our weight and expertise around from a manufacturer of all things. And now we're just applying that stuff into the additive scope, and it's been a fun ride so far. Yep. So, as the equipment manufacturer for this exercise, right, we're looking to enable, the 3 other parties that are represented in this conversation, right? So there's a lot of scope to what, we can offer, but there's 3 primary things I wanted to touch base on for the purposes of this demonstration. So really the first one is the actual machine platform that was leveraged for this development exercise. So we'll refer to it throughout the rest of the presentation as a 500 series platform, so the RenAM 500 series. Functionally, you can get those in single or quad laser variants. We'll get into that in more detail if there's any questions at the end, but it's essentially a 250 by 250 XY build volume with a 350 millimeter in Z direction, okay? So the system itself will leverage up to, like I said, 4 500-watt yttrium-based fiber lasers. The full-scale system itself will include its own internal closed-loop powder recirculatory process. So it does all the sieving, batch control, and management of the process gas stream for you inside the system. And then obviously, in the sense that it is intended to be a dedicated platform, we can obviously leverage 4 lasers across a very small working volume to be very highly productive within that working scope, right? We'll touch on some other technologies within that platform in the future slides, but that's just kind of the baseline for it right now. So as I had alluded to, in the middle of your screen now, we have this functionality for our larger scale systems called the reduced build volume. So functionally, if you look at the complete bounding box of that apparatus, it fits inside of that 250 by 250 by 350 millimeter build volume of the full scale platform. And what this allows guys like HC Starck and HiETA to do is leverage smaller batches of material volume from a developmental perspective and introduce them to the advantages of the 500 series platform without introducing the whole machine to a grade of material, right? As Paul had alluded to, there's many a times during developmental phases, you're going to get into situations where some alloy grades might not work the way you expected, right? So that's what the small batch trials for, small batches, 10 kilograms at a maximum kind of thing, allows you to run small scale development projects within that. So that's kind of on the hardware side, right? Definitely. The next and last final bit I'll talk on in this slide is the quantum. So that's Renishaw's build preparation software. So obviously it's going to do all the standard things. Again, I'll talk about it in more detail throughout the presentation, but primarily what it does is it enables the end user to have a wide variety of parameters, laser parameters, system parameters available to them. And they can functionally leverage this tool, the tools within Quantum, to manipulate any build processes that they may need to work with to help develop the system, the alloy, and even the design in some circumstances as well, right? So in conjunction with that, it also offers some clever utilities for a multi-laser assignment of the lasers as well. So that can get kind of interesting relative to metallurgical control as well, especially with refractory alloys, all right? So just to touch on some of the specifics of the RenAM 500 series a bit more detail, we tout, if you look at the CFD diagram on the right-hand side of your screen, we designed the system functionally around, at the end of the day, an intelligent gas flow system throughout the apparatus. So what you're looking at in the CFD diagram on the right-hand side of the screen is it's a flow diagram, essentially, CFD diagram of the internal gas chamber during the manufacturing process. So there's the volume flow rate gets split up into 3 primary sections, okay? So the 2/3 of it will come down from the top of the build volume by the lens and produce like a shower head effect, which keeps all the spatter, condensate, and all that bad stuff we don't want to be incorporated or blocked by the lasers away from the lens. And then there's an air knife that functionally rides adjacent to the build platform itself, which helps evacuate and remove all that spatter, condensate, and other particulate media away from the system. That gas flow is inert. Typically, it's leveraged with an argon gas, but it is also intercooled. So it's maintained nominally at a temperature of about 20 degrees centigrade. And what that allows us to do is maintain good thermal stability of the platform and, generally speaking, things like to condense more readily in cold air versus hot, right? So that's a good little thing. The system itself also has a vacuum purge. So to fill the vessel by itself, it's about 1,000 gas liters, but it's obviously would be substantially more to push out all the air in the chamber during the semi-prep process if we weren't to have a vacuum pull down prior to introducing any argon into the chamber. So that's pretty clever from a runtime capacity. The machine can be ready to go in about 10 minutes when you hit the go button, down to even like 500 ppm or less. One of the more clever things, and these even kind of harkens back to some of the stuff we've done with all of our other industrial metrology products, like our touch trigger probes. They're all based in the science of kinematics, kinematic loading and unloading. Okay, so the wiper blade in our quad system is similar to that. It would be the same in both the RBV and the full scale platform, in the sense that there is no operator intervention relative to leveling the wiper system. The optical control and the leveling of the optics are based upon a hard-coded position based upon where the kinematics are located. So the wiper mechanism itself can be loaded and unloaded with a couple set screws, or springs rather, So it's a very quick turnaround process for the operator. And then the last two images there, functionally, like I said, we do design and manufacture our own optical module. Okay, so it's what that has allowed us to do basically is have all four of the lasers in the quad version of the system to be isolated very close together, which allows us to maintain the same optical temperature across all the lasers. And then moreover, there's no stitching phenomena relative to their addressing of the bed platform, because each of them can address any portion, any of the lasers can address any portion of the substrate at any given time based upon the output demand that you program into Quantum, which is a software I'll talk about next. So much like a lot of build setup softwares, Quantum does a lot of the pretty basic things, right, relative to metal additive, what you would expect a slicing utility to be able to do. So you can import, orient, scale, label part geometries as you import them into the software. There's a couple of utilities built into the functionality of the tool for support generation. Quantum will leverage what's called column supports. It's a pretty common, node to node type support generation based upon overhang threshold limits that you define within the software. Right, so you can kind of see some contour maps of that shown in the upper middle image there. And functionally, then once you do design the build layout, it starts to give you a few more clever tools associated with, say, how much exposure cross section you're going to have per layer. Therefore, that drives how much laser on time you're going to have per layer, which allows you to start to kind of think about this in a bit more holistic manner relative to manufacturing efficiency, laser on time versus wiper on time. And even things about, abrupt cross-sectional changes, which will drive thermal histories, which can lead to things like cracking phenomena or, shift lines in the part, things like that, right? And one of the more powerful tools that, Charlie will touch on later in the presentation is the developmental protocols built in the Quantum. So it's bread and butter, in my, my humble opinion, really is its ability to rapidly iterate between parameter sets and any developmental protocols for new alloy systems. So there's over 170 parameters within Quantum. The common five, right, are power, hatch distance, exposure time, layer thickness, and point distance, right, relative to how you excite the laser onto the bed. So what's interesting about Quantum is that you can export all that stuff into a CSV file, copy and paste out of your DOE, whether it's Minitab, Excel, or some other form of your methodology, whatever is relevant to you. Copy and paste those values back into the CSV file, import it into Quantum, and then you're rocking and rolling. You didn't have to do anything else. So you can do a whole setup, one part, hundreds of parts in seconds, right? So that's great. Once the parameters are defined, you can create scan paths, right, which are relevant to the parameters you defined. It's either going to be single or multi-laser based upon what the application area is, right? So in that circumstance, relative to the multi-laser approach, you're going to be trying to ensure uniform utilization of all the lasers across the bed. So that's where some of that stuff, like I alluded to prior, like available cross-section comes into play as well, because cross-section is going to drive laser on time, right? And therefore maintaining a uniformity across those multiple lasers is really important. But yeah, that's really all I wanted to say about Quantum. There's a lot of tools. If you have any questions, let me know, and I'll pass it on to Charlie, who talks about actually using the software.
Great. Thank you, John. Very informative. Hello, everyone. I'm Charlie Burkett. I'm head of the Materials and Applications team at HiETA Technologies. I have a background in mechanical engineering from Exeter University and 7 years experience in the additive manufacturing sector, 3 years of which I've been at HiETA. So who are we? Who are HiETA? We are specialists utilizing additive manufacturing to reduce the mass and volume of mainly heat exchangers through design and materials work. We've been established around 8 years, based in Bristol. We have 2 offices, one of which is at the Bristol and Bath Science Park. We have our production facility there, as well as materials team and design team, but also a newly opened production facility in Thornbury, just north of Bristol, which is focused on our aluminium production, which you can see in the middle picture there. Around 50 members of staff, running 10 machines, varying architectures from, as John mentioned, RBV, single laser platforms that are more flexible, up to serial production quad laser systems. We cover the whole AM value chain for our customers, so focusing on design, materials, and production. design teams looking at 1D modeling, computational simulation, so CFD, FE, topological optimization, and all designs they do are validated through our in-house testing. The materials team, which is the area we're looking at today, is most part of the Resistojet project. And we've got an overview of our development process here, which we've applied to the STAR project here today. So powder comes in from HC Starck. We'll check the powder, conduct a literary review if needed, and start building our design of experiments using Minitab and Quantum, as John mentioned. We'll manufacture samples, measure those samples, starting on a small scale, usually starting with bulk density and scaling up from there. So iterating through the process and always having that end user and product understanding, in this case, the Resistojet in mind, to advance those developments forward. Next slide, please, Federico. So here are the results, I guess, and progress from the STAR project so far, mainly down to my fantastic team at HiETA. I certainly can't take all the credit for this. So we have at the bottom, I guess, the progress of how we've developed these parameters, starting off with density. So this is on the tantalum, pure tantalum alloy, 99.95% density achieved, scaling that up to focusing on the Resistojet. So can we build thin walls, single track scanning, and we've achieved walls below 300 micron. We then move on to more complex geometry. So we've got some single track scanning helical structures there, and again building still on the RBV platform to the eventually producing some successful tantalum Resistojets and tantalum alloys as well. So moving on, what's next? Before we go to Federico, who's going to talk about some of the testing done on those delivered units. It's probably time we start thinking about scaling up and moving off the RBV. And thanks to the scalable architectures that we have at HiETA, we'll be moving from the RBV into a full build volume, and then looking at the other processes involved. So this is really HiETA's pedigree here. We've got the validation of the material parameters that need to be done on a full machine, and looking at how the powder is going to be managed. We have some in-house machine calibration techniques for single and multi lasers that we've developed to make sure we're happy with the quality of the processing and, I guess, locking down streamlined processing on the machine. Post-processing wise, we've also got, you probably can't really see, but in the top right-hand corner, we've got automated powder removal rigs, and HiETA have addressed a number of points down the post-processing chain that are specific to the products we produce, and ensuring we've got the best post-processing as well in-house. That includes inspection and quality assurance. And finally, we've also got HiETA designed quality production management software to trace parts around the building using QR codes and formal routing of parts. Over to Federico.
Thanks. Yeah, so what about the testing then? So we have the parts, we test them, and then we soon find out that the models that we have been working on produce quite different results from the experiments. So here on the right, you see an example of multi-physics simulation of a Resistojet. So where you have the solid kind of wall of the heater, and the fluid going from the inflow and recirculating and going out from the nozzle. So you can imagine that that's a lot going on here. In particular, there are two main aspects of physics that we need to model, that need to be very careful model. The radiation, thermal radiation. So you can imagine that these elements are at very high temperature. So depending on the surface emissivity, you might have a very different solution of this thermal model. So surface emissivity is a key parameter to know. And secondly, also, this is a resistive element. So, for instance, you have an electrical potential applied to terminals, and then you have a flow of current by Joule heating or resistive heating, as you wish. The structure heats up. So you need to know, again, the electrical resistivity very well. So that's what we've done. We have performed some tailored tests for AM materials to measure these two properties of the metals. And also we correlated, in particular for emissivity, that with the surface roughness. So on the left picture, you can see a setup in the thermal vacuum chamber of a strip of metal, 3D printed metal, with instrumented with thermocouple. So this is like a typical ASTM standard for measuring the surface emissivity. And the center figure, you can see some SEM picture of the surface of 316 stainless steel and Inconel. And basically, we combine all of these into our parameter research. So in summary, on the left here, you can see the resistivity that we experimentally measured in gray, and that we found the literature for cast material, same material, in red. And you see that there is quite of a difference, and these translated very different results into the models. On the right, you see also the surface emissivity. And again, what we measured is relatively higher with respect to the cast material properties that we found in literature. And this is strictly related to the surface roughness. So we are conducting actually similar, same test setup for the refractory metal, so both for pure tantalum and tungsten alloy. I want to stress the fact that we didn't do this just to improve the models, but yes, to improve the models, but to then be able to use those to optimize the design of the Resistojets and really achieve the maximum possible temperature of the gas. Then, moving from the material testing, we performed, and we are still performing, a number of lifetime tests for the heaters. So on the right, you see an heater instrumented with thermocouples and placed into the thermal vacuum chamber of the University of Southampton. And what we have done basically is to cycle the heater from ambient temperature, so 20 degrees Celsius roughly, to in vacuum to the maximum operating temperature. So we have done this both for Inconel and we are doing it for refractory. And the goal is to demonstrate that this heater can hit the requirements for a typical mission. So in particular, we have been given from SSTL requirements for lifetime, roughly speaking, corresponding to 1 maneuver per day for 7 years of operation, roughly. And we already passed, let's say, the requirements for Inconel, and we have very promising results for tantalum and tungsten as well. So typically, you see in the chart in the middle, typically we're measuring temperatures and resistance, so that then we are able to trace any change in particular resistance that would highlight any degradation of the material. So currently, we are continuing the lifetime test on the heater, in particular on the refractory ones, with the goal really to meet those requirements that I mentioned before. And we are also already manufacturing the AM parts for the engineering model of thrusters. So we already have several parts in refractory, and we are doing not just the heater, but the complete assembly of the Resistojets that has an envelope and fittings and stuff. So the next steps are really to perform a full qualification campaign of the thrusters. So this is not just doing doing the lifetime test into the thermal vacuum chamber, but also doing performance tests where we measure directly the performance, so the specific impulse that I mentioned at the beginning of the presentation. Also, we do tests that we call environmental tests, where we replicate with the checker table the launch environment that varies for the specific mission that we are considering. And also we conduct other tests, including leak of the resistojet, leak tests, pressurization tests, and probably most importantly for AM materials, we do cleanliness verification, which means that we want to see how much of the powder and in what particle size is left into the resistojet before and after, let's say, the qualification campaign. This is a key because there are requirements from the mission provider. So the next step at the end of this project and with this big collaboration is to launch it. So to put a resistojet, a star resistojet into space and on a demonstration mission and prove that in its own environment, operational environment. Thank you for your attention, and now we can answer your questions.
All right. Thank you very much. Just a reminder to our live audience that right now is your chance to ask any questions of your own to this esteemed panel. We do have a couple of questions rolling in. Let's take this one first. Charlie, would you mind elaborating on your inspections and quality assurance? What are you verifying per each run versus what have you validated as being stable and therefore allowing for a lower inspection level?
So there's probably two main aspects to our, I guess, inspection. So there's the actual building of the components and the density of the material. So we're polishing, imaging samples, mounting, polishing, imaging, and ensuring we've got good density in both bulk areas, thin walls, and more importantly, some of the more difficult features of the component. So overhangs, looking at upskin, downskin, and ensuring we're achieving consistent density over each run. The other side to that is the production of samples for Federico and the team at Southampton University to test. So thermal, resistivity, emissivity samples that are actually quite difficult to manufacture because of how thin they are. So we've come up with some novel techniques to produce those samples and deliver to Federico for inspections, his side. So yes, I hope that answers the question.
Well, there actually is a bit of a follow-up to that. Were there post-processing steps for the Inconel to modify grain structures, surface roughness, etc., before the testing?
No, there weren't actually. One of the goals of the project is to ensure that we're producing resistojets at a competitive cost. So if we can get the parts off the machine in a finished state with minimal post-processing, that's a win-win. So we haven't done any post-processing. Heat treatment's probably a key one you're thinking of there. There's nothing too novel in the post-processing that we've done. We've tried to keep everything to within build to keep sort of lead times and costs to a minimum.
All right, next question. When do you expect the flight demo mission to take place?
That's a good question. So we don't have a flight demo mission set up. So basically that depends on the availability from our partner SSTL. So there is, let's say, the support from them to demonstrate this technology. So we look into the earliest into 2022 to make a flight demo. And just to a note for the technology readiness level of the technology, right now we are at 5. And by the end of the qualification campaign, we aim to reach TRL 6. And then from there, we will work identifying a flight opportunity and working on a flight model. So doing a bit more kind of strict qualification campaign on that, and then move up to TRL 8, fly, TRL 9, and then hopefully commercialization.
So, John, this question is for you. What are the challenges to print refractory rather than standard metals? And are those challenges so unique that Renishaw might be considering building a printer specifically designed for refractory printing?
Yeah, sure. I mean, Paul had alluded to that a little bit, and so did Charlie. But I mean, at the end of the day, the refractory materials, they have a high thermal conductivity. They have a pretty, catastrophic ductile to brittle transition temperature phase that can happen, and they have very high melting temperatures. So there's a couple things that we can do within the process to help try to mitigate for those potential failure modes that can result as a consequence of those three properties. All of which come down to the primary microconstituents built into the alloy system, right? So tantalum all day long, right? But as soon as you put a little bit of tungsten in it, it's going to start to fall off the cliff a little bit. So, and kind of what I had alluded to earlier in the conversation, being able to be a part of these efforts early on helps us to understand if the tools and facilities that we offer within the product line, including the software and any laser control that this end user has, it helps educate us as the manufacturer to understand if you can actually do what you want to do, with the equipment. So there's a couple things you can do inside the system to be a little clever, outside of a standard scan path generation, elevated substrate temperatures, to help mitigate for that transition zone, multi-laser alignment, welding the same spot on top of one another. Modifications to laser wavelengths, continuous versus modulated lasers. There's a lot of things we can look at there to help facilitate welding. Like I usually tell people that, melting's the easy part, solidification is the hard part. And that's just kind of how it goes for most materials.
Charlie, I wanted to ask you to talk a little bit about the challenges of reusing refractory powders in the AM process, which I would imagine would be crucial.
Yeah, that's a good question, Brent. And yeah, potentially quite a sensitive one as well. How reusable are the powders? So I think certainly for the refractory metals, tantalums we're working with, it is uncharted territory for us. Due to the throughput, we physically haven't seen that much powder being used as of yet because we're still on this RBV level. But we are obviously looking at the next step and scaling this up. And I think this is where HiETA's background and experience here really comes into play. We're running aluminium and Inco in quite high volume productions, and we're constantly monitoring the process emissions. HAZ, people might be familiar with, so the heat affected zone. This is the powder near the part, and moisture levels, which will affect the chemical composition of the powder, PSD, morphology, oxygen, nitrogen, hydrogen pickup. So all sounds pretty scary stuff, but it's things we're really starting to get a handle of and starting to understand in the process. And all this learning we've gained over the last few years will be applied to tantalum as we move forward onto a full machine. And it's really interesting material. It's very ductile. In metal terms, it's almost like chewing gum. A colleague said earlier, and the effects of O2 and other variables on that are going to be new to us going forward. So, yeah.
Question asking, what do you think would be the advantages of DED or directed energy deposition in this application? I'm not sure who would like to take that.
I can take a whack at it. I say that because in our additive manufacturing development here at Starck, we've looked at virtually every AM technique, whether it's powder-based or wire-based, for refractory metals. The big advantage that the powder bed systems have is it allows you to build very fine features. The DED techniques, any of the blown powders and things like that, you really cannot produce the fine features and the intricate details that are part of the Resistojets design. In that regard, DED certainly would not be suitable for this application, at least for producing the designs that Federico has shown. It might be useful for some of the other, I'll say, bulkier components where you're still going to have to do a little bit of machining to meet tolerances and things like that. For the Resistojet itself, I don't believe it would be suitable.
Okay. Next question is a good one. With regards to the 70% mass savings, what characteristics of the AM Resistojet's total system, including the propellant change tank, the jet itself, contributed what portions of the mass savings? Does that make sense?
Yeah, it's kind of a complex question, but so we can make an example with the SSTL platform, right? So if we consider to use the same sort of tank of propellant, so in that case we use xenon propellant, then let's assume that that's going to be the same, and what you're really changing is just replacing the Resistojet that they have. So the Resistojet itself weighs a bit more, especially if you use refractory metals, obviously. And also the Starck Resistojet requires a bit of extra electronics to operate the heater as you should. So overall, let's say electronics plus thruster weighs a bit more than the original SSTL Resistoject, but the mass that you're saving in terms of propellant is much higher. So you have like many kilograms saved because of the 70% more efficiency. Then this question is a bit more difficult to answer when we refer to other kind of missions. So it's really mission related, but in general, mass saving is related to the more efficiency and the higher ISP that the Resistoject can give.
All right. Paul, this is a question for you. Talk about the promise of additive manufacturing when it comes to expanding the refractory metal industry.
Well, refractory metals, as everyone is painfully aware, are extremely expensive compared to, I'm going to say, more traditional metals. Where additive manufacturing will allow us, I think, to expand refractory metal usage is in the fact that we're going to use a lot less of it. Some of the processing to make powders is very similar to what we currently do when we make traditional products. So being able to use a smaller amount of the material and produce components that you currently cannot produce at the moment because they're just too expensive in a traditional subtractive technique to basically hog out of a large chunk of metal. So I think the AM will allow us to produce things that, like I said, we currently can't produce or are too expensive to produce using traditional techniques.
Okay, we are getting close to the top of the hour, but we do have a couple of more questions that I want to try and squeeze in here. If refractory metals are advantageous, would ceramic be considered as a potential material candidate or a ceramic alloy?
Most likely no. One of the things that the Resistojet has to do is thermal cycle. So when it's just sitting around up there in space, it's going to be at cryogenic temperatures. When it's fired off, you're going to reach temperatures in excess of 2,000 degrees or what Kelvin or more. Ceramics generally do not hold up well to that kind of thermal cycling. So that's one issue. The other issue you have is building with them. They are even harder to build with in some ways than refractory metals, so that there would probably need to be a fair amount of development. And to one of Charlie's points, designing a machine for refractory metals, will be a challenge. For ceramics, it's going to, have more heat requirements and make it even more challenging. As far as alloys, maybe a Cermet or something like that would be a potential benefit, but that's probably going to be more metal than it is ceramic. So I don't really think ceramics would be suitable for this application.
Okay, we're right at the top of the hour. Let me just squeeze in this last question. We kind of touched on this a little bit, but I'd just like to hear the answer again. If all goes well with the qualification campaign and the environmental tests, when can we expect 3D printed Resistojets to be orbiting above our heads?
Yeah, I mean, as I said, hopefully by 2022, probably 1 year later, or who knows. But really here, the key is that Resistojet and this very high performance Resistoject have been not around at all. So is a stepping change kind of performance that we achieved here. And this will definitely enable new missions. So we'll enable, for instance, our partner SSTL to have much more flexible satellite platforms, to therefore have lighter satellites, or maybe have an extended maneuverability. And also one key aspect of this Resistoject is that each step that we went through into the design was looking towards scaling, so towards large production. So it is possible, and it's one of the key of this technology, because the heater itself, as we say, is a single component, is 3D printed, and for the dimension that this one has, you can print many in one single print plate. And hopefully with capabilities and extending capabilities of HiETA with Renishaw machines, we'll be able to produce many of these to address also constellations.
All right. Very, very good. Very interesting. That is all the time that we have today. Thank you to everyone on this panel for sharing this presentation and your insight with us. By the way, this presentation was recorded and it will be available on the IMTS Spark platform. If you're watching and would like to learn more, head over to Renishaw's showroom on IMTS Spark. And while you're there, be sure to add the presentation later today and next week's AM in-depth sessions to your MySpark planner. So that's it for now, and we hope to see you next week.